Hello, my name is Ryo Kaji from Section C, Professor Parker, and this is my Lab 2 motion of a falling object. So the purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. The object I chose was a yellow toy, and this is a peer review of my graph with the lines for observed position, gravity only, and gravity and drag. So for some introductions, for some models and fundamental physics principles, we use Newton's second law or the momentum principle with those equations, in which we can derive the net force from the equations for the updated velocity and updated position, and we use the gravitational force, and we consider gravitational acceleration as 9.8 meters per second squared, and we also use drag force, which can be used by minus b and magnitude of v squared times v hat. And the more surface area of an object, the more drag it has, and that's a drawing showing how the drag force contracts the gravity. So for my tracker analysis, this is the video that the tracker recorded. The system was a yellow toy, the surroundings were Earth and its air. The initial conditions were position 000 meters, velocity 000 meters per second. The mass was approximately 0.05 kilograms, and the total time was 0.5 seconds. And it was at 30 frames per second, which is why I computed. This is how the computer computes the change in position, and it was dropped at approximately 1.8 meters. This is my glow script code for accounting only for gravity. We can see here that I uploaded the j-hat vector, the magnitude of acceleration is 9.8, the ball position and ball velocity, the initial conditions, I put them here, the time until 0.5 seconds, which was I said before, calculated the net force using the formulas I showed before, and the velocity update and the position update. And this is my glow script code with gravity and drag. It looks almost the same as the other one, except for I added the proportionality constant for the magnitude of the drag force with a bunch of trial and errors, and try to find where the predicted model and the observed model matched, and it was approximately at 0.005. And I also accounted for drag, so I used the equations I cited before to calculate drag, and I added that to the force net. So this is my observed versus predicted graph analysis. The yellow line is gravity and drag, and the gravity only is the red line, and the observed position is the blue line. As you can see, the observed position and the gravity and drag are very similar, and the gravity only fell way faster than the other two, mostly because I'll explain the reason later, but it reached ground faster, as you can see. So the observed model and the predicted model that accounts for gravity and drag are very similar, but this is not the case when you compare them, the observed model with the predicted model that only accounted for gravity. This happens because we know there are a lot more forces other than gravity. There are other forces other than gravity in the surroundings of the system, and the predicted model with only gravity falls downwards faster compared to the model that has both gravity and drag, because the drag force is in the opposite direction of gravity, which makes its rate of descent decrease. And the curve for the observed model looks a little bit rugged due to possible human error while computing the motion of the object frame by frame in the tracker, or with faulty calibration, stake, or analysis misplacement. So for the what does this mean question, the model that accounts for gravity and drag will reach terminal velocity because the velocity looks like it has an asymptotic behavior, which will suggest that there will not be acceleration or net force because the forces of gravity and drag will eventually cancel each other out, which is why it reaches here. And for the what if question, I edited the glow script code and the initial velocity with -1 in the j-hat. So what happened is that the terminal velocity of the yellow toy is the same, but it will reach the terminal velocity faster because we basically threw the ball downwards initially, so it will reach the ground faster. In conclusion, in this lab, I used Newton's second law to predict the motion of a falling object considering gravity and drag. I used tracker to collect experimental data and glow script to make the computational models. And with the 3 models completed, I compared them and observed the differences, similarities, and addressed some possible human errors while producing this lab. Thank you.